All right, so in this video, I'm going to talk a little bit about ordinary annuities and annuity dues. So for an ordinary annuity, the payments happen at the end of each period. So what I have here is an example. In this case, it's 7 periods long, perhaps years, perhaps months, whatever the case may be. But I have an example that is 7 periods long, and there is a series of payments, which I've denoted by PMT, and they're all happening at the end of each period. So notice if I start at time 0, I go through a period, then I have a payment. I go through a period, I have another payment. I go through a period, I have another payment, so forth. So the payments are all happening at the end of each period for a specified number of periods. And so this is making this an ordinary annuity. If a couple of these payments were missing, so I had several payments, but a couple of them are missing in the middle. Let's say payment 4 was not there. So if payment 4 was not there, and I just had payments in years 1 through 3 and then 5 through 7, then the entirety of this would not qualify as an ordinary annuity. I could look at the first 3 payments as an annuity in that case, but I couldn't view the entire time period as consisting of an ordinary annuity. Now, if you want to find the future value of an ordinary annuity, it involves using a formula that looks kind of complicated. But let's kind of walk through it a little bit. So the PMT that we have here is the payment that's happening every period. The R is the nominal annual rate per year. M is the number of periods per year. N is the number of years. So if I have R divided by M, I have the rate per period. If I have M times N is the number of years, M is the number of periods per year. So that's going to give me the total number of periods. And I basically just plug things in and solve it out, and that's going to give me the future value of an ordinary annuity. Now, you can also do this with your calculator as well. So if you're using a calculator or Excel, basically what you can do is you can put in payment, the rate per period, the number of periods, keeping in mind to make sure that the rate per period and the number of periods are coinciding with the same length of time. So if you're working with monthly compounding, then the periods need to be the number of months, and the rate needs to be the rate per month, and so on and so forth. But you could plug in the payment, plug in a 0 for a present value, plug in the rate per period, plug in the number of periods, and then solve for the future value. And that would work fine too. And if you're doing this in Excel, you could do basically equals FV and put in the appropriate inputs within the function in Excel. Again, keeping in mind to make sure you put in the number of periods, the rate per period, the payment per period. So those 3 things have to line up, whether you're using your calculator or Excel. The number of periods, the rate per period, and the payment per period all have to line up with the same length of time. So if you're doing monthly for one, the other 2 have to be monthly. If you're doing semi-annual for one, the other 2 have to be semi-annual. Everything has to line up with the same length of time. Now, if you want to calculate the present value of an ordinary annuity, then there's another formula that I have here for you. And if you're thinking, well, that looks even worse, it is decently complicated. However, it's worth noting that if you kind of look at this and you work out the math a little bit, if you go back to a prior video, I showed how to calculate the present value of a cash flow, and it was the future value divided by 1 plus R over M to the M times N, right? So if I want to find present value, I take future value and I divide it by that value. Well, if you look at this, this was my future value up here. So one thing that's kind of worth noting is if I take that equation and I take that whole piece here and I divide it by 1 plus R over M raised to the M times N, then what winds up happening is this formula pops out. And basically you can work through the math on that, but all you really are basically doing is taking this whole formula here with this whole side of the equation, treating that as a future value, plugging that into that future value equation I showed in a prior video, and dividing by the 1 plus R over M, raised, that whole section raised to the M times N, divide that through, and what you wind up with is the present value of the ordinary annuity formula. Now, if we are going to kind of proceed from the ordinary annuity to the annuity due situation is one in which I would have the payments at the beginning of each period. So I have here the same timeline, the same number of periods, but I basically just shifted the payments over so that I have a payment and then I have a period, and I have a payment and then I have a period, I have a payment and then I have a period. And so because I have a payment at the beginning of each period, this is going to be an annuity due. And I have some formulas here, and you're thinking, well, that just looks kind of nasty. Well, it turns out this isn't quite as bad as you might think. Basically, if you think about what's happening with future value, we're finding the value we would have of all these payments at the end. That's the idea for future value, finding the value at the end of this timeline. Well, if I think about the ordinary annuity and the annuity due, the payments are all shifted one period earlier in the sense that basically I get a payment here and then I have a period of time, whereas for the ordinary annuity, I have the period and then the payment. So what that means is each payment for an annuity due is going to have an extra year to compound and grow. And so basically what I do to find the future value of an annuity due is essentially I just take that section right here, which is the calculation that I was doing for the ordinary annuity. And I just multiply it times one more compounding period's worth of interest, which would be 1 plus the R over M. So that's where this is coming from. I'm basically just kind of reflecting the fact that every single payment associated with this annuity due would have one extra period's worth of growth compared to the ordinary annuity. So to find the future value, I basically just provide one extra period's worth of growth. I'm multiplying the ordinary annuity formula by 1 plus the R over M. Now, if you want to find the present value of the annuity due, basically the present value will wind up being one extra period's more valuable. And the reason for that is if I'm finding present value, if I go back to the ordinary annuity, if I'm present value, I have to bring the value of this payment back to time zero, this payment back to time zero, and this payment back to time zero. And so if I'm doing that, basically I'm discounting. But if I'm looking at the annuity due, each payment is shifted earlier. And so each payment is going to have one period less of discounting that it's going to have to do. And so as a result, I basically add on a little bit more value by multiplying by the 1 plus R over M to the formula that the ordinary annuity has. So basically I take that ordinary annuity formula and essentially I undo a little bit of discounting by multiplying by 1 plus the rate of return that we're getting per period. So essentially it just gives me one more period's worth of growth. And if you're looking at that and you're thinking, I'm not sure I completely understand how that works, that's fine. But suffice it to say that these are the longer formulas you could use for this, or you could use your calculator or Excel to do that. But I'll come back to that point in a little bit. So I'm also going to talk in this video a little bit about perpetuities. So let's talk about perpetuities. So perpetuities are a unique case. Perpetuities are a situation in which you have an annuity. It's the same amount every single period for a specified number of periods. But here's the wrinkle. The wrinkle is it's an infinite number of periods. So the specified number of periods is it's infinite. So it just goes on forever and ever. So let me kind of walk you through a sort of a thought experiment or a basic idea here that'll kind of guide us to what's going on with a perpetuity. So let's suppose you put $1,000 in a bank account that was earning 5% just basic interest per year, okay? So simple interest in the sense that there's no compounding or anything like that within the year. So just simple annual compounding, nothing shorter than that. So if I took that $1,000, my present value, and I multiplied times my rate, 5%, so my present value times my rate, kind of give me my payment. So $1,000 times 5% is $50. So basically what would happen is I could start off with $1,000. At the end of the year, I'd have $1,050. I could take the $50 out, leaving me with $1,000 again. I could then leave it there for the next year, at which point I would have $1,050. I could take the 50 out, bumping me back down to 1,000. And of that year, I'd be at 1,050. I could take the 50 out, bumping me back down to 1,000. The end of that year, I'd have 1,050. I could take the 50 out, would bump me back to 1,000, and so on and so forth. So basically what that would mean is I could actually take out $50 at the end of every year indefinitely, forever. So we have same amount, $50, end of every period, forever. This would be an annuity. So in that example, I would have an annuity of $50. And the way I would get it would be by putting aside this $1,000 and the account getting 5% just basic interest per year. Now, because that's the case, we can actually rearrange that calculation. So if I come back to this, I have $1,000 present value times 5%. That's where the $50 comes from, right? So I can rearrange this and kind of know, well, if that's the case, and it is, if I want to find the present value of a perpetuity, Basically, I just rearrange this formula here. And what I'm going to wind up with is the present value of a perpetuity is going to be the payment divided by the rate. So I'm just going to take payment divided by rate to find the present value of a perpetuity, which is kind of cool because now I'm finding the present value of an infinite series of cash flows in a real simple calculation of just payment divided by a rate. Okay. Now, in this second formula that I have here, what I'm kind of just denoting here is that we might have a situation where the payment that's being quoted is perhaps monthly, the rate that's being quoted is annually. I'm just kind of noting here that you might have to adjust, just like I've talked about for some of the other calculations. You might have to adjust the rate to find the rate per period so that it would line up with the length of time associated with the payments. In other words, if the payment is monthly, the rate that's in the denominator needs to be a monthly rate. If the rate is weekly, the rate that's in the denominator needs to be a weekly rate. But ultimately, I'm just going to take the payment divided by the applicable rate as long as I've matched up the time frame associated with the payment and the time frame associated with rate. And that gets me my present value of this infinite series of cash flows in just one simple calculation, which is kind of nice. Now, if you're thinking about it, you might be thinking, well, wait a minute. So is that example an ordinary annuity or an annuity due? You know, what is that? Well, it would actually be an ordinary annuity. So think back to the example. $1,000 in the account. At the end of the year, I got 1,050. Take out the 50, right? Leaving me then with $1,000 and so forth, right? Which meant I took out the $50 at the end of the year, which basically means that this calculation that we have here is for an ordinary annuity. So if you think, all right, so that's an ordinary annuity, so I gotta shift the cash flows to find the present value of a perpetuity that's an annuity due. Well, there's an infinite series of cash flows. So even if you shift the cash flows one period forward, there's still an infinite series of cash flows because it's infinite. So really what that means is the only difference between the present value of an ordinary annuity and the present value of an annuity due that's a perpetuity. So ordinary perpetuity versus annuity due perpetuity. The only difference between those two would be the annuity due perpetuity has a payment at time zero. In other words, today. Okay. And so that's the only difference. Well, the value of $1 today, thankfully, is $1. So to find the present value of an annuity due perpetuity, I take the present value of the perpetuity that's an ordinary annuity, which is this calculation here, and then I just add on a payment. The reason why I can just add on the payment is because that payment that was missing for the ordinary annuity was today, and since $1 today is worth $1 today, I don't have to do any time value money adjustment to that, so I can just add in the payment. And that would be how I find the present value of an annuity due perpetuity. Now, a little note that I should kind of sort of toss in there here. I'm not going to belabor this point too much, but notice that finding the present value for perpetuity is payment divided by the rate, okay, the rate per period. If I go back, I have a situation here where if I rearrange this, I could pull this R over M outside and have payment over R over M, which would kind of be the formula for a perpetuity, right? So it turns out, basically, this formula here is built by essentially playing around with perpetuities and using the perpetuity formula and the regular time value of money formula to create a combined formula that finds the present value of this infinite series or this finite series of cash flows, I should say. And here's the brief sketch of kind of what's happening here. So in this case, it's a future value in this case. We also do the present value down here. So here's the basic idea of kind of how you do this. I'm just kind of sketch out the idea. And if you don't catch it, that's okay. It's just sort of a bonus topic that I like to throw out there a little bit, make you think a little about kind of where the formula is coming from. But basically, what you can do is I can use a perpetuity. I can find the present value of a perpetuity that goes on forever. Then I can find a perpetuity starting at some point in the future that goes on forever and find out the present value of that. And if I find the present value of a perpetuity that goes on forever and I subtract off the present value of a perpetuity that starts at a certain point and then goes on forever, what's left is the piece in between. So basically, I wind up taking the entire timeline, so present value of perpetuity forever. Then I take everything that happens after a certain point, find that value. By taking the value from everything, subtracting off this chunk, what I'm left with is this chunk. Now, if you're thinking that's just confusing, that's fine. Don't worry about it. But basically, the long and the short of it is by creatively playing around with using the perpetuity formula and the regular time value of money formula and doing some rearranging, basically what will happen is these formulas will pop out of that. So this formula is essentially derived from appropriate uses of the perpetuity present value formula and also the regular time value of money present value formulas. Okay. All right. Well, hopefully this little introduction to annuities has been helpful. Thank you so much for watching and have a great day.